Yes, Doctor.
Okay, thank you so much for the confirmations. So yeah, I'm very happy to see you again here. Yeah, and today allow me to continue our discussions on the topic related to gravitational quantum states. Yeah, my name is Rohim, and this session is the second sessions of the uh, my turn to deliver this topic. And first, I would like to review or summarize what we have studied in the previous week. Okay, in the previous week, we have studied about the bouncing particles in quantum mechanics. And we discussed the quantum bouncer system, which described the confinement system of particle trapped in a linear gravitational potential above a fixed floor. And this topic is quite interesting for me because theoretically it has been predicted by quantum mechanics, and you can find in several textbooks. And then experimentally, it has been confirmed by this research group. In the first time is in 2002, and then 2003, and so on. And yeah, this this one is the derivations in the framework of quantum mechanics. So we have Schrodinger equations with additional linear gravitational potential (MEZ) here, and then we have done with the derivations. We can see that the solution is given by the Airy function AI only, and then from these derivations, we also see that the energy is quantized, and also the trajectory, in this case is the vertical trajectory, is also discretized. I mean, the particle does not follow the continue trajectory, but the particle will jump from one height to another height. And yeah, and we also try to apply the result to the ultra-cold neutrons. This one represents the zeros Airy functions, as we discussed last week. And this column represents the numerical analysis. I mean, the exact result. And then this column represents the approximate result. And from the results, we can obtain the energy level for ultra-cold neutrons. In this case, I use the particle data group in 2020. Okay. At the end of the last week, at the end of the sessions, we briefly discussed about the relativistic particles, and yeah, maybe the content of today's discussions is related to this topic. So we will discuss the relativistic particle. At first, we will discuss the free particles, and then we will try to represent the quantum bouncing in the context of relativistic bouncing particles. So far, do you have any questions before we continue our discussions?
So far, no.
No? Okay. Okay, so yeah, there are several works which may related to the quantum bouncing particles in the context of relativistic particles. Maybe the first one I would like to mention the works by Alberto Sa and Marcelo Siever, which consider the bound states due to unaccelerated mirror, and also Nicolas Boulanger et al., which consider the Dirac particles in gravitational fields. And also maybe at the end of today's discussions, I will try to deliver some work related to relativistic quantum bouncing particles. But before we go to this topic, I would like to mention about the relativistic particles in a box. For example, the works by Alberto and also Alberto, which this paper consider the Dirac particle, and this paper discuss related to Klein Gordon and Dirac, and then this paper discuss about the Majorana fermions. So you can read by yourself the content. And yeah, today I will start by discussing this topic, focusing on relativistic particles in a box, because in the previous sessions we discussed non-relativistic particle in a box. We solve the Schrödinger equations for a particle confined between two infinite potential. Okay, so we will start. So we start from the Dirac equation. So this one is the Dirac equation. So we have I gamma mu partial mu minus m c equals to 0. So mu here start from 0, 1, 2, and 3. So if we expand, to the if we expand to the more explicit expressions, we will have these equations. So 0 here correspond to t component, and 1 correspond to x component, and 2 correspond to y component, and 3 corresponds to z component. And then gamma mu here is gamma matrices, and yeah, maybe I will discuss more specific, I will discuss more specifically later. And this gamma matrices satisfy this Clifford algebra. So gamma mu, gamma nu equals to 2 g mu nu. So g mu nu here is tensor matrix. So if we multiply gamma mu, if we multiply the first equations by gamma 0 from the left, we will have these equations. So maybe I should write clearly, I think. So gamma 0, from here we have a gamma 0 square, and gamma 0 square is equals to 1, and gamma 0 gamma 1 is equals to alpha 1, gamma 0 gamma 2 equals to sorry, I make mistakes. So this should be alpha 2, and this should be alpha 3. So this one gamma 0 squared equals to 1, the actual expression is identity matrix, and gamma 0 gamma 1 equals to alpha 1, and gamma 0 gamma 2 equals to alpha 2, gamma 0 gamma 3 equals to alpha 3 minus m gamma 0 c. And sometimes we write gamma 0 here as beta. And then if you see here, maybe I think I should replace the okay expressions, the correct expressions. Sorry for the inconvenience. One. Two. Yeah, yeah, this one is the correct one, I think. So I should replace. Okay, and yeah, this also should be changed. Okay, something like this. Yeah, and here can be seen as a Hamiltonian operator and equals to this one. And you may remember that minus e partial x equals to momentum operator x component, and this one corresponds to momentum operator for y component, and this part corresponds to momentum operator for z component plus m beta c. Okay, and then yeah, basically we in order to obtain the expression of c here, we have to solve the Dirac equations, and Dirac equations represents the equation for relativistic particles. Okay, maybe later we will try to solve these equations. And yeah, you can find the solutions in many sources. And here I use the derivations in our paper published in 2021 when we discussed the relativistic particle under chiral MIT boundary conditions. So, we consider the Dirac equations in Minkowski coordinates, which is given by this. We see these expressions as we show previously, where m is the mass of the Dirac particle and k here is the momentum. And here I use S to denote the spin orientations, and gamma mu here is a gamma matrices. And actually, there are infinite set of gamma matrices representations. And for example, if we use the gamma matrices in Dirac representations, we will use this, and gamma 0 is equals to this one, and I here is 2 times 2 identity matrix, and gamma I here is corresponding to gamma 1, gamma 2, and gamma 3. And the content is given by this one, where sigma A are Pauli matrices. And yeah, the Pauli matrices should satisfy the anti-commutation relations, sigma I, sigma j equals to 2 delta ij multiplied by identity matrix, and delta ij here will give the value of 1 when I equals to j, and will give the value of 0 when I differ from j. Okay, if we work in the Minkowski spacetime, the gamma matrices satisfy these anti-commutation relations. But if we work in general spacetime, we may write the this eta mu nu as g mu nu. And in this case, we use the eta mu nu equals to diagonal of 1 minus 1 minus 1 minus 1. Okay. So far, any questions? No, I think. Yeah, you can find. I think most of you already take the general relativity course, maybe. Okay, and then to solve these equations, we introduce the ansatz for positive energy solutions, like this, given in equation A3, psi equals to u exponential minus I at multiplied by exponential power I k x. So here I use dot here means if we have 3 spatial component, so it means that I k1 x1 plus I k2 x2 plus I k3 x3, where a here is energy, which is given by this, and u here is a 4 component Dirac spinor. So the solutions will be given by in proportional to 4 component Dirac spinor. And then to solve, we further decompose the UKS into the upper 2 component spinor. For example, here is KZ, maybe KZS, and latter 2 component spinor is KS. So it can be written something like this. So actually, you can also introduce the other symbol, but here we use KZ and Kai. KZ as the upper 2 component spinor, and Kai for the lower 2 component spinor. So in total, we have 4 component Dirac spinor. And then by substituting back the Dirac spinor A4, this one, into Dirac equations, so we substituting back the Dirac spinor into these equations. So we obtain the following two couple equations. So this one and this one. And if we decompose each equations, A5 and A6, you will actually find the four equations because Z and Chi here contains two components. So this one contains two equations, and this one also contains two equations. So in total, you have four equations. Okay, then here A5 and A6 associated with negative energy and positive energy solution. So this one corresponding to or associated to negative energy, and this one associated to positive energy solution. And then first we will focus on the in the present discussions we will focus on the solution for positive energy only, and which means that the Dirac solutions will be written as given in equation A7. So something like this. This one. So if we use only the equation A6 here, and then we replace the chi s. We replace chi s to this one. So if we move this term into right hand side, so we will have sigma dot k over m plus a. So something like this. And then this one is the Dirac solution for the positive energy. And NKS here corresponds to the normalization constant, which can be obtained by this one, equation A8. And we have to note that the two components minor KZS here is normalized by these conditions, and KZS here corresponds to the spin orientations. Maybe I will show on the next slide. So something like this. So in general, the two components we know ZIS consist of linear combinations of two components minor with a spin up Z directions and spin down minus Z direction. So T here stand for transpose. So we have Z plus Z equals to 1, 0. So if we write something like this, 1, 0. And for the spin down, it's equals to 0, 1. So in general, the expression for the two component spin order consists of these linear combinations. So alpha Z plus Z and beta Z minus Z. So because this one is given by this one, 1, 0. So alpha multiplied by 1 is alpha, and then alpha multiplied by 0 is 0. So this term contributes alpha 0, and this term contributes 0 beta. So if we take the summations between the first term and the second term, we will have this value, alpha beta. Okay. And then because ZS is normalized given by this one, so this two component spinor should satisfy these conditions. So because Z dagger multiplied by Z equals to 1, then we have alpha multiplied by alpha, and then beta to beta equals to 1. No question so far? So if you have any question, please feel free to ask me directly without waiting the Q&A session. And then if no, I will continue. And then the normalized two component spinor with spin orientations in the plus minus x and plus minus y directions are given by these equations in A10 and E11. This line corresponds to the plus x and minus x directions. And then plus this line corresponds to plus y and minus y directions. And then in general, the spin orientations can also be parameterized using the polar angle theta and azimuthal angle phi as follow, as written in this context. So if you have the value of c and theta, you can define the spin orientations, and then these conditions will determine the solution for the Dirac equations. Okay, I will continue again. Now we try to apply the our understanding on relative to the Dirac equation for relativistic particles in a box. So in the present discussions, I use this paper by Alberto et al., which published in 1996. Maybe I show you their paper last week, I think. So you can, yeah, this paper. Okay. So we consider the Dirac equation for a free electron of mass m moving along the z directions. So the Dirac equation is given by this one, and this equations is obtained from this one. So this one corresponding to the Hamiltonian operator, and minus I partial x or yeah, and y and z corresponding to this only 1 plus 1 dimensions, time and z dimensions. So in these expressions, we do not include the contribution from x and y term. So we only write this one, and this one, and this one. Okay. And yeah, you may notice that in this expression there is a c factor, but in this expression we do not have, because in this page we use c equals to 1, and in this paper they keep the value of c. Okay, then this one is the general solution that we obtained previously, I think from this one. And because this one is sigma dot k here is sigma 1 plus k1 plus sigma 2 plus k2 plus sigma 3 k3, because we only consider the 1 plus 1 dimensions, so we only have sigma 3 k3 here, and sigma 3 in this paper is written as sigma z and k3 as k. Also, you may notice that in this paper, they keep the expression of h bar, but in this expression we use the h bar equals to 0. Sorry, h bar equals to 1. We use the natural units. So before we go further, when we discuss the non-relativistic particles in an infinite potential, well, we can use the Dirichlet boundary conditions of the vanishing wave functions around the boundary. However, when we consider the Dirac equations, we cannot use the Dirichlet boundary conditions. Why? Because the Dirac equations is first order differential equations. So if we impose these Dirichlet boundary conditions, the wave functions will trivially vanishes everywhere. So we cannot use these boundary conditions. And then as an alternative, we may use the boundary conditions from the MIT back model. So these boundary conditions, this back model is originally described to is originally used to describe the quark confinement. So published by published in this research paper. So you can also find the extensions of this back model, which is known as chiral back model. So to discuss the relativistic particle in a box, we will not use the Dirichlet boundary conditions, but we will use the boundary conditions from the MIT back model. Okay, and yeah, sorry, yeah, this so be written in English. So this one means the boundary conditions from MIT back model. So it has the mathematical form, something like this. So we have I and mu gamma mu c equals to c, and mu here is for vector normal inward. So for example, if we have something like this, and then r here is the radius, and mu here normal inward. So this vector pointing out the area where the particle appear. So for example, if the particle appears here, then the normal inward go to these directions. Okay, and then from this mathematical form, it has two properties at the boundary surface. The first one is the vanishing of the normal current, and then the second one is vanishing of the scalar density. So as we mentioned previously, that for Dirac equations, we do not use the Dirichlet boundary condition. So the wave function here, the wave function, for example, if this one is the boundary condition, does not vanish around this area. State here. Maybe I will show you the derivation of this property later. I think there is maybe there is a page which show the detailed derivation of this property. Okay, and yeah, we are going back to discuss the relativistic particles in a bulk. So we consider the Dirac equations for a free electron of of mass m moving along the z direction, given by this one, and then the confinement system mass is written as a function of position mz. So in the non-relativistic case, we have this scenario, right? So the potential inside the confinement area should be zero, but the outside should be infinite. But for the relativistic particles in a box, so mass inside the confinement area, inside this, should be finite. For example, if we choose M here, and then the mass outside the confinement area goes to infinite. Then the solution for the solution for Dirac equations of a particle inside this confinement area is given by this one. So this one, these equations represents the superpositions of the right wave functions and then left wave functions. I mean, from this you can see that the k here and the k here has opposite directions. So inside this area, the solution is given by the superposition of the right moving wave component and right moving wave component and left moving wave component. Okay, and then to solve these the solutions should satisfy the boundary conditions at 2 points. The first point is at z equals to 0, and then the second point is at z equals to L. Then if you impose this boundary condition to the solutions at 2 points at z equals to 0 and at z equals to L, you will find that the momentum is discretized and satisfy these conditions, which is given by these conditions. And interestingly, if we take the non-relativistic limit, which is m is much larger, m is very large, so the this term will goes to 0. Then we will find that KL must be given by NP and pi, and n is given by 1, 2, 3, and so on, which is similar to the non-relativistic case when we discuss the infinite potential well. Okay. Yeah. And then if we discuss the probability density of such a system, we will have this one. This one is, so I use the figure from this reference, and you can see here that the wave function does not vanish at the surface as we mentioned previously. But if we take the larger L, the wave functions around the boundary surface will close to 0. And from here, for example, if we take L equals to 100 L0, L0 corresponding to H bar over MC in proportional to Compton wavelength, I think. And then if we consider the L equals to 100 L0, it already goes to non-relativistic limit, which is where the probability or the wave function around the boundary surface will equals to 0, which is given by Dirichlet boundary conditions. But if we consider the relativistic case, the wave function does not vanish around the boundary surface. Okay, so this one remain relativistic, and if we take the greater L, it will go to non-relativistic case. And yeah, previously we discussed the system under MIT boundary conditions. And yeah, of course, the MIT boundary conditions is not unique boundary condition that guarantees these properties. I mean, there is more general boundary conditions that remains guarantee this property, the vanishing of the normal current. For example, if we discuss using the chiral MIT boundary conditions, you can also discuss the Dirac particle in a box. But maybe today I will not discuss this topic. Maybe in another chance, maybe we will have it. Okay. Any questions so far? If yeah, I hope you can understand what I deliver. Okay, please.
Also good, Doctor. Doctor, may I ask, can you go back to the previous slide?
Okay, this one?
Yeah, the n, right? The tangent KL approximately to 0, the n, right? Can it be 0? The n.
Pardon me?
The n equals to 1, 2, 3.
Uh-huh.
The n, can it be 0 also?
Zero. Zero. I think the lowest, the ground state is n equals to 1. I think
Oh,
because
the n is the uh,
because if n equals to 0, the energy must be 0. I think.
oh, so
Okay, so the minimum energy is not 0. So and the minimum state is how to say, the minimum state is given by n equals to 1.
oh, the n is the energy level.
N correspond to the state. I
Oh,
mean the ground state, first excited state, second excited state, and so on.
the principal quantum number, right?
Hmm.
Oh,
I think
all right.
maybe I can show you. Oh, please wait a moment. Okay. 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 So this the ends similar to maybe in analogy to these situations. So in the context of non-relativistic particles, the energy in proportional to n square. So if n equals to 0, so the energy equals to 0. So the minimum states should be given by n equals to 1. Is
Oh,
it okay?
yeah, understand.
Okay,
Oh, thank you.
thank you. Any other questions? Maybe before we continue. Okay, no? Okay, then allow me to continue the discussions. Yeah, okay. So basically what we discussed today is most of them based on the research paper, I think. Yeah. So also this one is also based on the research article. So you have comments or suggestions. It remain open, I think. So 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 if you are interested in, I think it is also nice to discuss. Okay, the next one, the previous one, we discussed the relativistic particles in a bulk without any external potential. And then the next one, we will try to discuss the gravitational quantum states for relativistic particles. So these discussions, the next discussions based on this article, so published in 2021. And yeah, maybe for today, I will focus on the case of Dirac particles, but maybe the contents is mixed to the other kind of particles. So yeah, basically when we want to when we want similar to the what we discussed last week, when we want to investigate the confinement particle under the influence of gravitational potential, we can add the external linear potential to the Schrodinger equations. But so in this context, we can add the external potential to the Dirac equations, right? But in this work, we do not do such a scenario. Instead, we discuss the systems for rest particle with accelerated mirror. So this is where we use the equivalence principle here. Okay, so this panel corresponds to the non-relativistic bouncing particle that we discussed last week, and this panel corresponds to the relativistic bouncing particle that we will discuss today. So a particle in a linear gravitational bouncing on the floor at rest in Minkowski spacetime. So the K here is the particle moving under the linear gravitational potential, and then the floor at rest. And this scenario use a free particle repeatedly caught and bounced by uniformly accelerated mirror. So you can see here the difference at the situation of particle and the situation of the mirror. And to discuss the uniformly accelerated mirror, we use Rindler coordinates here. And then in this panel, we use external potential, V equals to MEZ, and working on Minkowski coordinates. And the contribution of acceleration A here is absorbed in this coefficients, exponential to xz d eta. Okay, and then by comparing this scenario, we can obtain the corrections to the energy level and transition frequencies. Okay, and then what is the Rindler coordinates? And Rindler coordinates is coordinates for an accelerated observer in Minkowski coordinates. So if we the Minkowski coordinates is given by t, x, y, z, and in Rindler we have eta, x, y, and z. And if we see in 1+1 dimensions, for example, in the Minkowski is given by t and z, and in Rindler is given by eta and z. So we can obtain the Rindler coordinates using these transformations. So this one is T and Z is Minkowski coordinates. Basically, it can be divided into 4 area. This area, and then this area, and this area, and this area. This area corresponds to the Reich-Rindler space, or Reich-Rindler, Reich-Rindler, and this one corresponds to the left Rindler, and this one corresponds to future Kastner, and this one corresponds to the past Kastner. And Minkowski metric is given by this one, And if we use these transformations, we will obtain the Rindler metric. And this Rindler metric will be useful when we want to solve the Dirac equations. Okay, and then maybe I will skip if there is a chance, maybe I may briefly mention this one. But yeah, okay. Yeah, similar to the what we discussed previously, but if we want to consider the boundary conditions for Dirac particles, the Dirichlet boundary conditions cannot be used. Then alternatively, we may use the boundary conditions from MIT pack model, which is the mathematically given by this one. And yeah, this one is the maybe the more detailed derivations to obtain the properties that we mentioned previously. So from this, if we take the Hermitian conjugate and multiply with gamma zero side from the right, then we will obtain this one. Maybe I should write in clearly. I think. Okay. 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 Sorry. So first we take the Hermitian conjugate. If we do something like this, then this shall be this one. And this one, right? And then, okay, I should. Okay. See. Okay. And you may also check this one. And yeah. Okay. Then we next use this one equals to, sorry, equals to 0. So this one is written by this one. Okay. Something like this. Okay. And then multiply by gamma 0 C. Gamma 0. I have something like this and something like this. And yeah, for the next one, we use this one must be equals to identity matrix. Something like this. Then this one, something like this. And then, okay. This one minus this one. Okay, right? And then the second one is if we multiply from the left per say times like this, then we obtain this one, this one. Okay. So yeah, you may also check. Yeah, I will check again later maybe. If I found some mistakes, maybe I will send you note, I think. But maybe I think there is, I think that it is correct. So this value equals to this value, right? Then this must be equals to minus per sine. So this is taken from this equation. So something equals to another something, and for example, this one is A equals to B equals to minus B. So which means that A and B still be equals to 0, right? So this one at the boundary surface. Okay. So okay. Okay. So we have this one. So this property means that the normal probability current at the boundary surface is 0. So normal probability current is given by this one, and the scalar density at the boundary surface is also equals to 0. So scalar density is given by this one. Okay, any questions so far? No? Okay. Then I will try to discuss the Dirac bouncing particles. So as we discussed previously, that in order to obtain the expression of relativistic bouncing particle, we solve the system in Rendler coordinates. Rendler coordinates is coordinate for accelerated observer in Minkowski space. And Dirac equations in Rindler coordinates is given by this one. And gamma tilde here is gamma matrices in Rindler coordinates, and capital gamma is spin connections. And yeah, as maybe I already mentioned that basically you can work in any representations, but in this work we firstly discuss using Majorana representations. So C tilde here is see the solutions in Majorana representations, and you can transform the solutions to the other representation, for example in Dirac representations and the solution for the Dirac equations in Rindler coordinates can be found in several references. For example, in this work, so you can also see the solution in this paper. And the solution is given by modified Bessel functions. So k here is a modified Bessel functions, and maybe this one. So this one is the comparison of the modified Bessel function k to the Airy function ai and bi. So the black solid is Airy ai, this one, and the dash red is bi, and dash green is modified Bessel function. And you can see that the general features of the modified Bessel functions look similar to the Airy function ai. So it goes to 0 as the growth of z here. Okay, and then if we impose the boundary conditions from the MIT plug model that we discussed previously, this one, to the general solution, then we will obtain these conditions. Okay, so be equals to 0. Then we can obtain the energy by solving the zeros of modified Bessel functions. And for this purpose, I use the Mathematica. We use the Mathematica software, and then find the solutions. And maybe in the next page, I will show the analytic expression for the zeros of the modified Bessel function given by this one. And if you see this figure, that the zeros modified Bessel function, it does not continue. So because only, for example, if we consider this modified Bessel function only, it is given by this one, this one, this one, this one, and so on. So it does not continue along Z. So it means that the energy is quantized. Yeah, you can also do the same things as this graphic. If in this figure, it is only given by a single modified Bessel function k, but in this expression we have the summation of the two modified Bessel functions, this one and this one. Yeah, you will find the similar we have here, I mean, but different value. So the energy will be quantized. And interestingly, in the non-relativistic limit, the energy level reduces to that of the Schrodinger equations in a linear gravitational potential. Okay, and then you can also see the work by this K, which consider the Dirac particles in gravitational field. Okay, then yeah, because yeah, maybe we can keep this one. Yeah, we can skip this one because we do not discuss the Klein-Gordon particle. So we may focus on this one. For the non-relativist particle, we have know that the energy corresponding to the zeros of Airy function AI, and then for the Dirac corresponds to the zeros of the modified Bessel functions. And then we can compare these two energy level. Okay. This one is the energy level of the Dirac Ponting particles. So if we solve these zeros of the modified Bessel function using this reference, so you can check the literature, this reference. Yeah, we obtain these expressions. And this one is for the non-relativistic Ponting particles. So this one corresponding to the Schrodinger equations in a gravitational field with an ideal mirror, where the boundary condition is given by Dirichlet boundary conditions, and this one, the boundary condition is given by the boundary conditions from MIT Bach model. And you can see here, if you take the non-relativistic limit, the energy cover this energy. You can see the first term, but we have this additional term. And this additional term can be understood as relativistic corrections. And the behavior is will be negative for few low states n, and shift to positive for the sufficiently large states n. And when the states is relatively low, then this term will be dominant. So the corrections will be negative, but when the states is relatively high, the positive term will be dominant. Okay. And yeah, this one is the comparisons for the non-relativistics and Dirac. D here stand for Dirac, and M stand for Majorana, and KG stand for Klein-Gordon. But we have not discussed Klein-Gordon and Majorana yet because we skipped these two particles. And yeah, the last few energy levels of Dirac Ponting particles are lower than ones of non-relativistic Ponting particles, and shifted to be larger for sufficiently large states n. Yeah, this statement also consistent with this statement. So maybe this one it come from these contributions. When the n is low, then this will be dominant, so it will be lower than non-relativistic ones. But when n getting large, sufficiently large, then the correction will be positive, so it will be higher than non-relativistic ones. And yeah, the energy spectrum cannot be directly observed in laboratory. I mean, the observer, the variable that can be measured in laboratory is transition frequencies. So we may also investigate the transition frequencies between we may calculate the transition frequencies of Dirac particles to be compared with the non-relativistic ones. So if we see here comparison to this one, the transition frequencies of all relativistic bouncing particles are higher than those for non-relativistic bouncing particles. So this one, yeah, this is quite interesting. And in this table, we use this value m over a equals to 10. And then how about if we apply it to the ultra cold neutrons? So if we use the data from particle data group in 2020, and we apply it to the Dirac, the corrections in the order of -20, which is quite small sense technology. And if we apply to the positronium, which is the mass is lighter in comparison to the neutron mass, the relativistic corrections will be around 10 power minus 19 hertz, also remain quite small to be detected. Yeah, this one, if you see the comparisons of the probability densities of the, for example, if we consider the non-relativistics and Dirac is given by the dash green, and non-relativistic is given by solid black. You can see here that the non-relativistic case is 0 around the boundary surface. This one, it corresponds to the corresponds to the Dirichlet boundary conditions of the vanishing wave functions. And if you see for the Dirac case, the wave functions or the probability density does not vanish around the boundary surface. This is corresponds to the MIT boundary conditions. Okay, then I would like to summarize for the for the present discussions. If we the transition frequencies, if we consider the relativistic bouncing particles in the context of Dirac particle, we found that the transition frequencies between two quantum states are greater than their non-relativistic limits. Sorry. And yeah, and the different properties of eigenenergy may be associated with the different boundary conditions that we impose. Okay, sorry. Okay. Any questions so far? Hmm? So if you have any question, please feel free. Yeah. Okay. What we discussed previously is for Dirac bouncing particles, and you can how to say you can also do the same things for the Klein-Gordon bouncing particles. Yeah, if you consider the Klein-Gordon bouncing particles, then you can also find the corrections to the energy level of non-relativistic particles. But if you consider the Klein-Gordon bouncing particles, the boundary condition is simpler. I mean, similar to the Schrodinger equation ones, because Klein-Gordon and Schrodinger equations are second order differential equations. So basically, there is no problem if you if you impose the Dirichlet boundary condition of vanishing wave functions around the boundary surface. Yeah, and then yeah, and of course you also can discuss the system for Majorana bouncing particles, and yeah, you can find the Majorana wave functions by using the linear combination of positive and negative energy of the Dirac wave function. And then because the Majorana wave functions also derive from the first order differential equations, so it will face the same problem, similar problem to the Dirac particles. And then you can employ the boundary condition from the MIT back model, and you can find the how to say the energy level for Majorana. Yeah. Then you can compare the energy of each particle to the non-relativistic ones. Okay. Okay. Hmm. Any questions? No. Yeah. Yeah. I hope you you enjoy the lecture. Sorry if my how to say my my teaching is not clear enough. Sorry, but I hope you can you can take some message from our today's discussions. And yeah, I remind you all to again to fill in uh, the attendance form. And yeah, before we close, if you don't mind, I invite you all to turn on the camera, and then we will take the picture. Okay. Okay. Okay, Nurul, Tirnisha. Okay, I will take the picture. So please. Okay, 1, 2, 3. Okay. Thank you so much, guys. And yeah, you will have I think the final meetings next week, right? So yeah, I hope you enjoy this program, and maybe see you again in the future. Thank you everyone, and bye bye.
Thank
Thank you,
you.
Rohim. Thank you, Rohim.